Hello. Hello. Okay, so welcome back to the afternoon session. And the first speaker of this session is Rajat Gupta. Rajat has received his PhD under the guidance of Professor Atul Dikshit at IIT Gandhinagar. Then he held postdoc positions at University of Texas at Tyler and Institute of Mathematics Academia, Seneca, Taiwan. And currently, he's a fixed-term lecturer at University of Maine, USA. And today he's going to speak about summation formulas from classical foundations to harmonic mass forms.
Thank you, Abbas Bhaiya, for a nice introduction. First, I want to thank Professor Shankhadhar and Professor Ajit Bhand for inviting me and giving me a chance to present my recent work with Professor Olivia Beckwith from Tulane, Nicholas Dementis from Nottingham, and Larry Rowland from Vanderbilt, and Kalini Thalagoda. So Kalini is a postdoc of Olivia. But I'll start from the very basics of the summation formulas. There will be summation formulas you may have seen already, and there will be some other summation formulas which you may not have seen, but here we will explore some of them. And then we proceed to the theory of harmonic mass form, which already very beautifully by Professor Nick Anderson and Griffin already explained the theory, and some of the speakers also talk about the theory of harmonic mass form. But my talk will be mainly focused on the summation formulas, which hardly been explored in this direction. There is only one paper by Larry with some Raji, Lee, and Diamantis where they explore the summation formula, but that was not a complete summation formula, which I can say. So, so let me start by giving some three of the summation formulas which are very important in analysis and number theory, and especially in combinatorics, people who work in partitions, these formulas are also very, very important to finding the asymptotics. First is the Poisson summation formula, which already Griffin has explored and gave the nth dimension version, like higher dimension. So this is a very basic formula where you're summing f of n at n every integer. And in the right hand side, you have a Fourier transform, which you're summing also at every integer. You need some conditions to have the convergence. You can have a Schwarz function, which is smooth function, and it decays very fast as x tends to infinity for all n. This summation formulas, which Griffin already told how you can use that, but the very basic use is, oh, by the way, this is another summation formula for finite sums, which is have an integral transform in the right-hand side, is a cosine transform, Fourier cosine transform. So this summation formula is very much helpful to derive the functional equation of Riemann zeta function. We all have seen in our number theory textbook that you can prove this functional equation by taking f as k to the n square here, means doing some transformation with some change of variable. You will have a theta transformation, and then you can use it to prove functional equation. Here, this is a usual Riemann zeta function. Oh, I forgot the region of convergence. Of course, it is real part of s greater than 1. Now there is another summation formula which is quite famous, Euler-Maclaurin summation formula. So I'm giving you a particular version of it. There are several, so I'm just picking up one of it. So suppose f and its all derivative goes to 0 as x tends to infinity. And then we have the following version of the summation formula. Here you can see in the right-hand side, you have an infinite sum and an integral with some finite polynomial involving Bernoulli numbers. And in the right-hand side, you have an integral involving a Bernoulli polynomial at fractional part. So how we can use this? This formula is very much useful to extend the region of convergence for for Riemann zeta function. How? Take 1 over x to the s for real part of s greater than 1, satisfies all the condition. If you put this 1 over x to the s here, you will get this integral representation. Of course, this is true for real part of s greater than 1. But if you further explore this integral, you can show that this is also convergent for real part of s greater than 0. So that's how you can define Riemann zeta function for real part of s greater than 0. And of course, there is a functional equation which is for all of s, and we're excluding s equal to 1. The next summation formula is very important. There are several reasons. First, the people who work in physics, this formula is very, very important, especially in the theory of Casimir effect. So this formula is like a 200-year-old back, 200-year-old. So in 1820, Plana gave the following, consider these phi of z as analytic function for real part of z positive. And suppose these series and the integral converge. Okay, suppose you put some conditions here that phi of x plus iy times e to the minus 2 pi y, limit y goes to 0, and this integral also goes to 0 uniformly as x tends to infinity. Suppose if you have these conditions in your hand, then Plana proved that take a limit n tends to infinity of this sum and this integral, and here you have an integral which is rapidly convergent. So I have very less idea about the Casimir effect, but I have the overview that what they do is that they have the two plates, non-conductive plates, then there should be some energy between them, and that energy is computed by this sum and the integral. And to get the energy rapidly converged means find the better approximation. This formula is very, very useful. But in mathematics, in number theory especially, I should say, we hardly see any application of it. Okay? But before going over that, let me first give the version of Abel just after 3 years after what Plana gave independently. He proved this following summation formula. And if you're wondering what is the application in number theory or in maths, here is the application that you can prove Hermite's formula for Hurwitz zeta function. So Hurwitz zeta function is an extension of Riemann zeta function, and this integral representation gives you an analytic continuation for every s except s equal to 1. Why? Because this integral, you can show that it is entire for every s. That's why this is very important formula. That means suppose if you will see in the next coming slide that if you suppose you have L function over Cus form, can you define Hurwitz's L function? Okay, so this question we addressed in this paper with Madeline Dossi, my postdoc supervisor, ex-postdoc supervisor at University of Texas. We just submitted this paper a month back, where we showed that if we take, so by the way, this formula was very general. I'm just giving you special cases. Suppose f is a Cus form over SL to Z. Take a between 0 and 1 and define this Hurwitz L function, an over n plus a to the s. Then we showed that this integral, this Hurwitz L function is nothing but this integral. And you can actually show that this is entire. And if you're wondering what this sigma 11 is, this is nothing but this series involving Bessel K functions. I'll just briefly sketch the idea that if you see 1 over e to the 2 pi t minus 1, think of it as a special function attached to Riemann zeta function. Now suppose if we have a L function over Cus form, this 1 over e to the 2 pi t minus 1 has an analog. And we have developed this theory of this analog in this paper, and then we showed that you just replace just 1 over e to the 2 pi t minus 1 with sigma 11 by this sigma delta defined like this. You can show that this is analytic in the whole complex plane except s equal to 1. Now, here you can see that you have, oh, by the way, this is entire, that means there's no pole, similar to what we have in the Cus form case. However, the striking property happen here is that if you take Rk of n, counting number of ways of writing a positive integer and sum of k squares for k bigger than 2, for example, R2 of 4 is 4, that means just say 2 square plus 0 minus 2 square plus 0, take all the combination. Then you can again define the zeta function over that, and this is absolutely convergent for k bigger than k over 2. This satisfies a functional equation like we have in the case for Cus form. And why I'm particularly mentioning about this functional equation again and again, because you will see in the summation formula, which I'll show you in the later for harmonic Maass form, the functional equation plays a big role. And by the way, that functional equation was proved by Professor Shankhadhar and Ranbir, both are sitting here. So if you use this functional equation and define this zeta function again, you have this integral representation. But here something interesting is happening. If you see, you have a non-zero term here. And because of that, you will be having a poles. That is, if k is even, that means if you are taking R2 of n, R4 of n, R6 of n, you will be having a finite set of poles, 1, 2, up to k over 2. However, if you take k odd, you will get infinitely many poles. So the parity, based on the parity, the location of poles is completely changed. Here you have from 1 to k over 2, that side. Here you have k over 2, k over 2 minus 1, k over 2 minus 2, and k over 2 minus 3. Okay? But I will not go into too much of the detail, but this is how you can use summation formulas to construct or generalize the L functions like I did here, like we did here with Professor Dossi. Now let's go back to the summation formulas. Let me give you a good introduction. I'll try my best to motivate you why do we need the summation formulas for harmonic mass forms. So the Ramanujan tau function is defined like this. Tau of nx to the n, it is given by this infinite product, or the power to the 24, mod x less than minus, mod x less than 1. Again, you can define a L function. It satisfies a functional equation. We have all seen that. So Hardy, what Professor Murthy was talking about, a lecture series of Hardy which he gave in the Cambridge. Here he mentioned that the functional equation must have been familiar to Ramanujan, but it was first stated by Wilton, not by Ramanujan. So let me give you a few formulas from the Hardy's lecture. So in page 161, he was considering the theory of this tau of n developed by Ramanujan, and he showed that theta transformation satisfies that if you have tau of n e to the minus nx, you have 2 pi over x to the 12, and you have a left-hand side with minus 4 pi square n over x. It's like tau goes to minus 1 over tau. In page 174, he proved another summation formula given like this. That is, if you replace this n by square root of n, here the right-hand side is completely changed and it turned out to be kind of an analog of Hurwitz-Zeta function. And that's how I got the idea in the previous work. Yeah. What are you saying? If you don't have a cusp form? IISER, no, I don't think so. With with transformation, this kind of formula exists, but the summation formula, no, because it has minus n to infinity to infinity. Yeah, you have it. Yeah, because that also satisfies a functional equation, but yeah, it doesn't have such kind of summation formulas. And here he concluded in page 184 that he considered this sum, n less than equal to x tau of n, which is equal to x to the 6 tau of n over n to the 6 j12 4 pi root nx. This j is a Bessel J function. So we'll be seeing this kind of sums later. After that, Chandrasekharan, in his seminal paper in functional equation and Dirichlet series, he actually observed that you can show that these all three summation formulas are nothing but equivalent to this functional equation. That means you can prove these, through these summation formulas, you can prove the functional equation, and from the functional equation, you can prove all these summation formulas. But he considered a more general class of Dirichlet series, which I'm defining it here. Suppose take an and bn be two sequence of complex number, not identically zero. Set these two Dirichlet series. Suppose you have an and bn two complex numbers. Define a Dirichlet series like this with some region of convergence. Of course, an and bn has a polynomial growth, by the way. Lambda n and mu n are two sequences of positive integer. Think of this as an integer n. Each tending to infinity, sigma and sigma a star are finite abscissa of absolute convergence for these phi and psi. Assume that phi and psi has an analytic continuation to the entire complex plane except some poles, finite set of poles. Especially in the case of cusp form, you have no poles. In the RK of n, you have only one pole. So all these are examples of this class. Then for some delta positive, phi and psi satisfy this functional equation. So this is our class, that if you have, this is Chandrasekharan's class, by the way. So if you have phi and psi two Dirichlet series, suppose they have an analytic continuation to the entire complex plane except some poles, and suppose the functional equation satisfied, then he proved more general theorem that extension of these three formulas for a class of functional equation, and he shows the equivalence with this functional equation. I'll give it later. So this is one example of it. Take a cos form, weight 2k, define an L function. It has a functional equation. And if you take an and bn is equal to like this, lambda and mu n is equal to n, delta is equal to 2k, that is a weight, then it is an example of it. How these summation formulas looks, as I said, they showed the Hackett's functional equation is equivalent to 3 general identities, which are very useful for the work which I will present. So the first identity is this, that you have this kind of theta transformation. Here P of x is just the residues. Whatever the poles you have, compute the residues with this chi of z, the left-hand side of the functional equation. Next is this result, where again you have a right-hand side and you have a more general kind of a Hurwitz L function kind of a thing with delta plus rho plus half as a power. And this is again as a combination of residues coming from, by the way, this is a contour, and the residues coming from this set. But I'm interested in this kind of resummation. That suppose if you have a an as an arithmetic coefficient and you multiply x minus lambda n to the row, this sum is called resum. Here you can see Chandrasekhar and Narasimhan showed that this thing is nothing but this series involving Bessel-J functions plus some main term, which is collection of residues, where these residues are coming from here. That means this contour is just encircling all the poles, calculate the residues, put it here. Yeah. So lambda and mu n are just defined as here in the Dirichlet series, and they goes to infinity. So if it is hard to visualize what's going on here, just think of that we are working with the cos form or Riemann zeta function simply, okay? So here where I was, in this, you can think that if I take a cos form, and as suppose Ramanujan tau function, this q rho becomes 0 because there is no pole. So you have an exact identity. Okay, and the validity of this formula can be extended up to this range, but this is a kind of a trade-off. If you extend this region, you lose the absolute convergence. So you fall into the conditionally convergent part of it. Okay, but you can actually extend, and it needs a lot of work. You have to use lots of trigonometric identities and theorem of Zygmunt and all sort of those things. We'll talk about it later. But now let me motivate you why I'm studying what I'm going to present here. So it's based on the asymptotics of these coefficients, which is already known. So Chandrasekhar and Narasimhan, they showed that in the very different paper, that if you have this range, 2 sigma a, if you're wondering what sigma a is just the L series defined on a of n, or sigma a is the abscissa of convergence for the L series defined of a of n. Then you have the following bound. If you put an is equal to tau of n and rho bigger than half, then you have the following bound. By the way, they also proved the omega result. Okay, but I'm just giving you this result only just so that I can motivate you for the work I'm doing. Okay, that means the important part is that you cannot put rho equal to 0, which was the aim, by the way. You cannot put rho equal to 0. If you put rho equal to 0, you'll get the asymptotic for n less than or equal to x tau of n. However, why I'm considering R3 of n? Because it is connected to Hurwitz class number, which we have all already seen for 3 days. Okay, so let's talk about that. Let me give you this special case. Take R3 of n, sum of 3 squares. Examples are here. R3 of 1 is 6. It's like 1, 0, 0, minus 1, 0, 0. Take all the combinations. Then this formula was proved by Chandrasekhar and Narasimhan that for rho bigger than 1, you have the following bound. And if you see here, this is the best possible bound for rho bigger than 1, because if you see, for rho equal to 2, this straight line is very straight. Okay, by the way, this graph is the ratio of this and this. This is the first main term in the formula. Once you do that, if you see the blue dots are rho equal to 0. That means for rho equal to 0, you just get a very highly oscillatory terms coming from this Bessel-J's, because you have cos and sine in the asymptotic expansion. Because of that, you cannot extend this to rho less than 1. And that was the result of the Shankhadhar. But now, what we see here, suppose if you have h of n, who is class number, which Professor Ono, Griffin, Nick, and other speakers, also one of them talk about these things. It has a few, I'm just giving you the list of some values, that for h0 is -1/12, 1, 2, 3, you have all these values. Then this h of n grows. For 10,000, this value doesn't go very far, but it stays there nearly between 180. So we should be asking ourselves that what is the growth of h of n, which is already, people know all about these things. So the growth is given by n to the 1/2 plus epsilon. This is, I picked it from Walker, but I think it was already known previously. So this was given by Walker in his beautiful paper where he proved summation formulas for correlation of Hurwitz class number, that is a shifted convolution sum. We'll talk about it. Here is what happened if you divide it by n/2 plus epsilon, like take epsilon. See what happened? It's just going towards 0 slowly, slowly, slowly. Right, and by the way, why I'm showing this code to you, it's not a mistake. Here, this Hurwitz zeta n was not defined in the Mathematica, and Professor Beckwith did a very hard job to defining this in the Mathematica, so I'm just giving that there. Now you have a code for Hurwitz zeta n. Huh? Y-axis is just the value of the ratio. It's like you divide this thing, it's just there. These are the values, and these are just, if you increase this n as 1 to the infinity, it goes there. Now, my question is this. Suppose so this is the result by Gauss, I picked it from Mortens, and that R3 of n and h of n are related by these congruences. And we have already seen the growth rate of these R3 of n and the resum. And the Walker consider these kind of summation formulas with shifted convolution. H of n plus L has the following main term and the error term. By the way, this C is a constant and L is a positive integer. But if you sum this n less than equal to x h of n, this also grows. So my question in this talk would be, what is the best possible bound for this one? N less than equal to x h of n. And we all know, since we are here for 3 days, that this h of n comes as a example of prototypical example for harmonic mass form. So we should use the theory to find the main term. Oh, the error term or the main term. So my aim would be to make this graph like this, to have some kind of convergence there and have some bound. So question, there were no result for the n less than equal to h of x, and especially the Rees type sum, because you have already guessed, to get the Rees sum in the way of Shankhadhar, you need functional equation. And these functional equations have been hardly explored, but thanks to these two, Professor Shankhadhar and Ranbir, they did a good job to prove the functional equation for harmonic mass forms, but in particular for polynomial growth. So let me define, which I've already defined there, that suppose 4 divides n, take a half integer weight modular form. Why we need a half integer weight? Because we need an example of weight 3/2. Take f h goes to c. These are the conditions to f to satisfy to call as a harmonic mass form. That is, has a modular transformation, Laplacian is 0, polynomial growth at all cusps. We denote this space by EI of S. We are just following the notation of Professor Shankhadhar and Ranbir. And if we take f as a holomorphic function, this just becomes a modular form. Now, this is the Fourier expansion. We have already seen that f tau has the following Fourier expansion for the polynomial growth. As you can see, there are no negative terms here. Here are the lemmas I picked from their paper and some of our paper, that if k positive, this Einstein space is just nothing but a modular form. We also need the growth condition. So suppose if we want to define a L function, and we all know that some of the harmonic mass form do have an exponential growth, so what we are limited ourselves to, the polynomial growth, so that we have a polynomial growth in the coefficient so that we can define a L function suitably. So for that, we need some the growth on these a plus n and a minus n. So this result by Shankhadhar and Singh, they showed that for negative integers, this space, the function which lying in this space has the following growth. It's just big of 1. In our paper, we want to extend it to the k less than 2, but we want to only include half integer weight case. Oh, sorry, including half integer weight case. So we also showed that k is equal to 0 and 2, and if we take k half integer less than 2, then c plus n and c minus n, the coefficient coming from the holomorphic part is c plus n, non-holomorphic part is c minus of n, they both grow polynomially. And the proof is very similar, that you apply a ck operator to this f, you get into the cusp form, then the cusp form has the polynomial growth, you conclude from there, then you have d of 1 minus k, apply all these operators, follow the same method. It's not hard to show that these are polynomial growth, very similar. Here is the result of Zage, which I already seen, that h of tau is given by, if you define h of tau is like this, then this is a weight 3/2 harmonic mass form over gamma 04. This first two terms gives you a mock modular form of weight 3/2, which we just saw in the morning. And this is a non-holomorphic part. Now, we should have a functional equation, right? So let me give you a good background, like how this thing happened, like what is the history of these L functions. So it's very recent. In 2014, Brinkman, Fricke, and Kent studied an L series for special cases of harmonic mass form, that is a weakly holomorphic mass form, weakly harmonic form, and but they were not able to prove the converse theorem. Because the way they were defining the L function, it includes, I think it includes this incomplete gamma function, which is not allowing them to prove the converse theorem. But the success was made in 2021 when Professor Shankhadhar and Singh wrote this paper, an analog of Wales' converse theorem for harmonic mass form for polynomial growth. They showed that you can construct a L function, L series for the harmonic mass form for the polynomial growth. Because we have just seen the result of them, that the coefficient are bounded by 1. They have a big O of 1 growth. So you can define an L function. But very recently, the recent development, that in Diamantis, one of our collaborator, Lee, with some Raji, Roland, they proved the L series for the general case. But if you're wondering how you can control the polynomial growth, you just put the L, they just use the test function. They apply the test function in the coefficient side. They use the, what is it called? Laplace transformation to get the nice L form series, constructed a functional equation, and they proved the converse theorem. So it is already known for exponential growth. So now this is the theorem of Chandrasekhar, the first part, second, Professor Shankhadhar and Singh, the second part is ours, that for k belongs to z, f, if you operate with the free convolution, then you all lies in this space. However, if you have 1/2 plus z, proof works similarly. I think in the case of kz, if you define this L function, let me give, where are the L functions? It's there. Okay, let me give you an idea, then I'll go back to the previous slide. So this is how the authors, Professor Shankhadhar and Ranbir, define that you take the L function for the coming from the holomorphic part, take a plus n over n to the s, take the non-holomorphic part, a minus n over n to the s, and combine these two. Because separately, they don't have a functional equation. Yeah, thanks to Ranbir who told me about this. And so they don't have a functional equation, so you have to combine them to get the functional equation. So here also it happened very similarly in the half case. It just you have to worry about the splitting of the integral. That means this gamma f of s has to split into integrals, which Shankhadhar and Ranbir successfully were able to do that. But in half integer case, proof works similarly. You can split those integrals for k less than half, for k less than 2. Once you do that, and by the way, this is W nu function defined by them, and it is given by this integral with incomplete gamma function, which you can easily write in terms of incomplete beta function. Okay, now let me go back to this. That's how you can show that you can also lie in this Einstein space with this chi bar. If f tau is given by this, g tau has a free convolution. If you apply the free convolution to f, it has the following transformation. Now we have the polynomial growth. Now we have all these free convolutions, and f lies in the harmonic mass form. Now it's just to rest. Now it's just left to construct these L functions the way these two authors constructed. So for real part of s bigger than maximum of mu f plus, mu f minus. By the way, this mu f plus is the growth of the analytic part, or what do you call, holomorphic part of the harmonic mass form, A of n, A plus of n, and mu f minus is the growth of the non-holomorphic part, that is A minus of n. If you have these things, you can define this completed L function, and you can show this functional equation. Very similar to what these two authors showed. Now, it's true for half integer weight that for if you define a completed L function like this, then it must have a pole at s equal to 0, 1, k minus 1, and k. Here are the residues coming from this Fourier expansion or these completed L function, and then you have a functional equation. So now we are in the same page of where Chandrasekhar Narasimhan were. If you remember, they were using the functional equation to prove the summation formulas. Okay, and so we partially solve this problem, means up to here. So yeah, Shankar then proved the negative integer case, by the way. So let me state some hypotheses and let me briefly explain you how these things works. So this is harmonic mass form, this is free convolution of it, G. Okay, as we have already shown that A plus minus n has a polynomial growth, B plus minus n also has a polynomial growth. Rho is bigger than rho naught minus half. Here rho naught is the maximum of these things for k bigger than 1, and for k less than 1, you have the following growth. Okay? So if you have this condition on rho, here is our summation formulas. Here is a summation formula that the left-hand side involves the resum for the holomorphic part, because h of n, if you remember, is the holomorphic part of the weight 3/2 Einstein series, 3/2 harmonic mass form over gamma 0, 4. So we should be interested in this. Here, this part is coming from the non-holomorphic part, and that really troubles us while proving some asymptotics, but we kind of manage it. Q rho is the collection of the residues at 0, 1, k minus 1, and k, and these are the two terms. If you see this term, this f nu is defined like this. Oh, I'm sorry. This is n. I just copy-pasted from the other paper. Yeah, this is n. Mu n is just n. So if you see, and if you recall the Chandrasekharan theorem, these two parts were already there for the modular form. And these two extra term is coming from the non-holomorphic part. And this is Q rho as a residues. Okay? Now, here is the Q rho. Explicitly, you can evaluate like this. And if you see, it just involves the Fourier coefficients at 0 of holomorphic and non-holomorphic part. So this is a very good example to see how you can use some classical theorems, a very old theorem of Chandrasekhar Narasimhan and several others, to prove such kind of summation formulas. And very soon we'll see the application of it, why these are important. Here the G n rho is arising because of this W function we have. Because the beta integral, you can write it as, oh, let me write a definition. So the beta integral, you can write it as 0 to a. Oh, where should I write? Okay, think of this as b of a n a b or x a b. So I'm writing 0 to x, 1 minus, oh, t to the a minus 1, t to the b minus 1 dt. So you can use this integral because this has an analytic continuation. It has a functional equation sort of. I'll show you how. I'll show you how it looks. So this G rho is nothing but this integral. But when k is not an integer, then you have this thing, which is completely analytic, because this has an analytic continuation with have some poles here and there, but it won't bother us to prove the asymptotics. Especially in the case of holomorphic modular form, this A minus N goes A minus N and B minus N both get 0, you will get back to the Chern-Shekaran's result. So you not only use their methods, but you also extend their theorems. Now, here is the asymptotic. That you have these two terms in your hand, then Q rho, here is the error term, and here is the residual term, and the main term is coming from here, Q rho. So for k less than 2 and bigger than 1, we have the main term as rho plus k. For k equal to 1, you have rho plus 1. For k less than 1, you also have rho plus 1, the main term. But let me show you how graphically it varies and why it is important. So to apply or to get the special case of Hurwitz class number, you need an expansion of G when you apply the free convolution. Right? So we use the theorem of Zage that H, if you apply a free convolution to it, it converts to H and this E3 half of 0, which is given by this. So I just took this theorem from their result as it is. This you can do a Fourier expansion, which Zage already did in his paper. Now once you use that and carefully combine all these terms, you will find that A plus N, that is just the original F we have, is h of n. This is square root of n 4 root pi when n is a square, otherwise 0. Why we have this condition? Because if you see in the whole non-holomorphic part, you had qn square of the coefficients. So the term only survives at n squares. So when n is a square, you have this term, otherwise 0. Now, once you apply the free convolution and use the theorem of Zage, you will see that b plus n can be given by this. This is the L function over characters. This t of n, by the way, is a kind of a Dirichlet convolution of some Mobius function. And it was a very big sum, so I didn't wrote it here. But if you're interested, you can look back to the Zage's work. It's a very long term, but it doesn't have a growth. B minus n, 1 plus I over a to 2 pi square root of n, when n is a square, otherwise 0, because you see b minus n is again a non-holomorphic part of the free convolution when you apply to the f, and similarly you have all these. So from here you can see that mu f plus, mu g plus is half plus epsilon, which I've already shown you by the work of Walker. And these terms just constitute nothing, it's just that you can get mu f minus and mu g minus, negative is just half because of, you see, all these terms. So now we are ready with the special case. We have all the bounds in our hand. We have our summation formulas. We have our growth conditions. Let's apply this formula, and that's how you get. So this rho naught is just get 3 half. If you put it there, it will just become 3 half. And here is the half coming from the absolute convergence. So you subtract, you get. So this formula, we have able to show that it is for rho bigger than 1. We have this resum and the main term. And it is a growth of 3 half plus rho for rho bigger than 1. But ideally, what our aim should be is that put rho equal to 0, which we cannot put here. But here is some striking observation we found. If you plot these things in Mathematica, then you'll see for rho equal to 2, the convergence is very nice. No oscillation, it's just going perfectly there. However, if you pass rho less than 1, you still have a better convergence. It still goes to 1. So from the graph, it is evident that the asymptotic holds true in the range of rho positive, which we are not able to show. We were only able to show for rho bigger than 1. But we did apply the theorems of Zygmunt and Chern-Shekaran-Simmons to extend the formula for rho positive, but again, it's a trade-off. If you go away from the region of absolute convergence, you lie in the conditional convergence where you cannot do such computations. But our graph is pretty much evident that this should be kind of a closest bound. Okay, since it is not proved, so I'm not claiming that, but I think it should be. We extend the numerical computation to see what happened at rho negative. Does it have a very weird behavior like we have for R3 of n? Here is for rho 0, you see. You have some oscillations here, but after that, it just goes to 1. What I'm trying to say is 1 here is that you take this re-sum, divide it by the first term, it should go to 1, right? If our formula is correct. And that's what happened in the rho less than 0. Oh, sorry, for rho equal to 0. For rho less than 1, you still have a kind of an oscillation because we are now in the conditional convergence range. You still have the oscillations, but still it goes to 1. And now you see, for rho minus half, it just goes weirdly. But it's still sometime, means it looks like it goes to just 1. So we notice that although the asymptotic behavior of negative rho is generally similar to rho positive, the pattern of oscillation is completely different for the rho positive case. Because for rho bigger than 1, we have the formula. We have the evidence that this formula exists, so we have this bound. But once you go past the absolute convergence, this just oscillates. But it's not similar to R3 of n, where R3 of n was just all the way here and there, because that was the best possible bound, which Shankhadhar and Narasimhan predicted. But in this case, you see, it seems like it goes to 1. At least you can predict for rho equal to 0, which we are really interested. But unfortunately, we were not able to show that. It needs some more techniques, maybe more analytic techniques, more classical techniques, which Shankhadhar, Narasimhan, Bachner, Koshlikov already did. So this is what the result I have to show you. But now, to conclude the talk, let me just give you the proof, how this proof works. So as I said, functional equation is the basic thing. If we have the functional equation, we have the summation formulas. And since after my PhD, I have been involved in proving summation formulas, kind of involved myself into how these summation formulas behaves for general class of arithmetical function, custom, as I already showed you for Abel Plana. So this technique was actually by Shankhadhar and Narasimhan, but we modify a bit because we have the holomorphic and non-holomorphic part. So consider this range, mu f plus minus is the holomorphic and coefficient coming from holomorphic and non-holomorphic part, their growth. Mu g minus is when you apply the free convolution, you get the holomorphic part, non-holomorphic part, their growth. And if you have the weight with alpha between these range, then you can write a plus of n like this, simple, L f plus. But now here we use the completed L function, gamma f of s. This gamma f of s was a combination of L plus and L minus. Now you can use that to write like this. Once you have, so now you're only left to compute these two summations. This is very familiar sum, we will see that. But this one is little different because this is a new special function. And we have already shown in our paper that it is very, very similar to gamma function. It has the same growth. It has almost nearly a complete functional equation. So you can use the theorem of Shankhadhar and Singh because they have the functional equation which already extended, but ideally it's their functional equation in the negative integer case. Apply those theorems, use the Cauchy residue theorem, then this first term is nothing but this. Just take out the residues and left with k minus alpha with this complete gamma L function. Once you have that, this Q rho, you can easily compute those things. And this complete gamma function part gives you rho, and this part, here we have used the functional equation. Now, once we have the functional equation, you can just do a change of variable for s goes to k minus s. Then you get lambda g of s. Here in this range, our Dirichlet series are absolutely convergent, so we can take out those Dirichlet series. Some will be out. You're left with the integrals with gamma function, and people who like gamma function and special function, they can easily see that this is nothing but Bessel J. And this is new stuff. So this gamma nu, this W nu, which are defined by these authors, is you can write like this, and you see here, it has a S, W nu of S. Just if you forget about this term, it has a kind of a reflection formula like a gamma function, but you just have a correction term here. Now if you use all these things, you have this integral, these two, and this gamma over gamma rho plus k minus s gives you the Bessel J. And to compute these integral w1 minus k, you use the representation in terms of these beta integrals. You can see that beta integrals, I took it out. You just left with gamma factors, which is again Bessel J function. And then you can show that a very similar result like we have a Perron's formula. If we have a gamma here, it just b of n x minus n to the rho. But now if you have this special function w1 minus k, it just turned out to be this g rho, which doesn't look nice, but it helps us to complete our summation formulas in a closed form. So this g rho of n is defined like this. However, for k not equal to n, as already explained, you can give it a closed form. And combining all these theorems, we have our summation formulas. And for the asymptotic result, since we have to work with the absolute convergence, so in the range of the absolute convergence, you can use this very famous bound of j rho, j nu, that is x minus half. Combine all these results, you'll get our asymptotic formulas. But the main question, all the authors of this paper, Olivia, Nick, and everybody is just wondering how to just do not have this rho thing in the resum. Can we find a formula for n less than equal to x h of n? And we actually have a hint, and and I'm sharing to all of you that there is a paper of Wilton and Hardy. If you see the very first slide, first couple of slides, I showed you a formula for tau of n. There was no rho in there. So they showed this formula completely different. But that approach, I don't know if it works in this harmonic mass sum case, but we are still figuring it out. So yeah, with that, I'll conclude my talk, and yeah, thank you so much for listening.
Okay, so are there any questions or comments?
You applied summation formula other than Hurwitz class number
Yes.
somewhere else?
Yes, we did. So we applied to the negative half integer case. Yeah, we took the Eisenstein series, and we also did the negative integer case, like what you guys work on. Yeah, we did. But since this was what Nick can already talked about, there's a more interesting formulas. Yeah, but if you read our paper, there are more and more asymptotics for other harmonic mass form, what Shankhadhar and Ranbir studied, negative integer case, and for negative half integer case too. Yeah. Yeah. This summation? The first half, okay, let me go back to this. Yeah, Apple Planner 1. Yeah. Yeah, but their integral representation was not there. So we tried to get the integral representation part. And why this is important, let me tell you, just in a quick words, that my whole goal is like to suppose for Riemann zeta function has a special function attached to it, like gamma function, another function, right? So my overview is that to see the L function is that for every, like we have the Riemann zeta function and the special function attached to it, for every L function also, there should be some special function attached to it. Like for Riemann zeta function, we do have the formula. So this is not the only result, this is just a special case, but the only result, so we have this result, right? E to the 2 pi x minus 1, d of x for real part of s less than 0. So now, if you have the Cus form, we were able to show in our paper that this is nothing but sigma of this delta minus 1 rho comma x dx. So we just showed that when we developing the theory of this analog function, that this just comes as a very nice special case. You just put 1 over x plus a to the s, you just get the integral representation, which is for similar to what we have for Hurwitz zeta function. So yes. This one? This one? Yes, this do come from, but for this L function, no, not easily. But I don't think for L function you have such kind of representation, just with e to the 2 pi x minus 1. You may have a different representation, but not like this, for real part of s less than 0. Yeah, yeah. Mm-hmm. 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 Yeah. Yeah. Mm-hmm. Yeah, that may. Yeah, of course. Where k by 2 minus n? When you're doing for cusp form, okay. This one? Yeah. Mm-hmm. Yeah. Mm-hmm. Mm-hmm. But yeah, I'm not saying that this has not been done. It's just that you don't have an integral representation in that sense. That is what, yeah, okay. But yeah, definitely I'll read the. Yeah. Yeah. Sure. Mm-hmm. Okay. Okay. Yeah. Professor Murthy's paper? Okay. I'll definitely look into it. Yeah, thank you. Yeah. Uh-huh. Uh, I think it was here. No, it was not here. Oh, it was last. It was last. Here? Here. Yeah. 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 Yeah, you can plot those graphs also. Yeah, it will have a similar behavior, but once you go past like less than 0, it just have this kind of a weird behavior we are having here. Yeah. Greater than 1. What our formula is saying that for greater than 1, we approve that. But for, you can see that row positive also has a similar behavior. Numerically, you can see that. Yeah, but it has not been proven yet. Yeah, yeah. Big O constant? Yeah, it is kind of a big O of n to the 1 half plus epsilon. Oh, constant. Constant, I don't know. We have to look at the Walker paper. I just means they should have, but I don't think so. It just, I think Walker also just write h of n as big O of n to the half plus epsilon. I don't know about the name if it has. Yeah, yeah, definitely. Oh, that's what you're asking. I was thinking that you were asking exact constant. Approximate, yeah. For epsilon, it depends.
question. So let us thank the speaker.